Hi! So far I have done 2 videos of this UNI-T UTS3060A signal analyzer, and I have demonstrated quite a few measurements using the spectral analyzer and some of the options the UTS3000A series offers. And in those 2 videos I showed you some of the techniques for observing weak signals. I demonstrated phase noise measurements, and I also showed you how to use the signal analyzer to demodulate AM, FM, and quadrature amplitude modulated or QAM signals. Be sure to check those videos out if you haven't done so already, and I'll provide links to those videos in the video description below. Of course, the UTS3000A series is extremely feature-rich, especially with all the options that comes with this loaner unit. In this video, I'll show you how to use this signal analyzer to measure third-order intercept point. And very conveniently, the UTS3060A has the advanced measurement option built in, and it will make the TOI measurement very easy, which I'll show you in just a little bit. Before I do that though, let's actually quickly review what TOI is and why it is important. So the main concept here is not that difficult to understand. Let's say we have 2 signals that are relatively close to each other in terms of their frequencies. If these 2 tones pass through an ideal system, obviously we would expect the same 2 frequencies coming out, except perhaps they are stronger than before if they pass through an amplifier. But in real world, there's always going to be some nonlinearity associated with amplifiers. So as the 2 signals go through the amplifier due to the nonlinearity, intermodulation products would be present at the output. Let me actually try to explain on paper. Alright, let me try to illustrate this. So let me set things up. Here we have the frequency, and here we have the amplitude. Now, for example, if we have 2 frequencies here, let's say here is FA, and here is FB. And of course, if you pass through a linear system, obviously the output will still be FA and FB. But if the same signals pass through a nonlinear system, of course, you have all sorts of products at the output. At the output, you will have, for example, FB minus FA, which is here, and perhaps FA plus FB, which is further out here. Of course, you also have the harmonics, for example, the 2 FA here, and 2 FB. So these are some of the frequency components. And what I have shown you here, these are the second-order intermodulation. Now, when the original 2 fundamental frequencies, FA and FB, are close together, like what I have shown you here, the frequencies of these second-order products are pretty far from the original frequencies, so they rarely cause any problems, as they can be easily filtered out. Now let's actually take a look at the other intermodulation products. Besides the second ones we just mentioned, there are also third-order products. So for example, we have, let's say right here, this would be 2 FA minus FB. And here we have another one that's going to be 2 FB minus FA. So now you can see probably why we're very interested in the third-order intermodulation products, because these are very close to the fundamental frequencies. And because they're so close by, filtering them out is actually not always possible. And of course, some people probably still don't understand why we have all these terms here. Now, let me actually briefly show you the mathematics behind it. Of course, I'm not going to go in depth because this is not a signal processing course, but hopefully you'll have some better understanding after I explain to you. To keep things simple, let's say we have 2 sinusoidals. One is A, and we can write it as E, J, omega A. Of course, we're not worrying about any of the amplitude and phase differences. Let's just keep it simple. Let's have a unit amplitude here. So basically, we're only worried about the frequency here, which is omega A. So then we have another sinusoidal, which is B, which can be written as E, J, omega B. Now, if we pass these 2 signals through a nonlinear system, we would have, for example, output, the second order, which is going to be A plus B squared, right? So of course, if you do the calculation, that will expand to EJ omega A plus EJ omega B squared. And if you just simply expand that, that would equal to EJ2 omega A plus EJ2 omega B plus 2 EJ omega A plus omega B. And that's where the term omega A plus and minus omega B comes in. Of course, if we do the third order, that's going to be EJ omega A plus EJ omega B cube. And then we have the E3 omega A plus EJ 3 omega B plus 3 EJ2 omega A plus omega B plus 3 EJ2 omega B plus omega A. Anyway, that's just the mathematics behind this. So let's actually come back to our diagram here. So the close proximity of these signals is obviously one issue, but here's another issue. As the amplitude of the fundamental frequency increases, so do the amplitudes of the third-order products. And because these are third-order products, the slope is 3 times that of the fundamental tone, because the third order is a cubic function. So if you take the log of that, you get a slope of 3. Why is this a problem? Let's actually plot it out. So here I'm going to draw you the relationship between the input amplitude and output amplitude. So let's say we have here is input, so it's amplitude in, and here is amplitude out. For fundamental frequency, essentially is, let's just say 45 degrees, because we have essentially when we increase the input, the output increases linearly, at least mathematically, that's the relationship. Now let's take a look at the third order product. Of course, it also increases as the input amplitude increases, but as I mentioned earlier, it increases at 3 times the speed of the fundamental frequency. So essentially, we're looking at the diagram like this. And because the slope of the third order products is essentially 3 times of the fundamental frequency, at some point you can see that these two lines will intercept at this point here. When these two lines intercept, the original signal and the third order signal would have the same amplitude, and you will no longer be able to tell these signals apart. Now, in reality though, the amplifier will probably saturate long before these two lines intersect. And you will often hear the term 1 dB compression point, and that's where the transfer function is no longer linear and output is compressed by 1 decibels compared to the ideal output. So for example, here's our input to output relationship, and that's linear. Of course, at some point, as the input amplitude increases, the output will no longer be able to keep up this linear relationship, and therefore it will saturate. So for example, here, it gradually saturates. And the 1 dB compression essentially saying that the point where, for example, here, the actual output is 1 dB down from the ideal linear output. So that's our 1 dB compression point. So obviously, we want the value of this intercept point as high as possible. In practice, this means that the magnitude of the third order products can remain low during the normal operating range. So yes, that's the theory behind the third order intercept. Now let's actually take a look at the real world scenario. All right, here's the setup. I have 2 signal generators. One is my HP8642B and the other is my HP8671A. And both of these generators are set to output 2 GHz. Because they're running with independent clocks, the output frequencies are ever so slightly different. The output signals are combined using this Wilkinson combiner, and output from the 8642B, you can see here, currently is set at roughly minus 9.5 dBm. Of course, I chose the amplitude so that these 2 signals are pretty much matching the amplitude. And of course, I also attenuated the HP8671A's output so that I get roughly the same amplitude between the signals. Of course, we can't see just much yet, so let's actually further reduce the resolution bandwidth here. So let's change it to, let's say, 10 Hz, and see if we can see anything. So now we have a center frequency of 2 GHz with a frequency span of 100 kHz, and the resolution bandwidth is 10 Hz. And you can clearly see we have these 2 additional tones. These are the third order products that I mentioned earlier. So let's actually do some measurements here. Let me enable the marker, and let's actually mark the center frequency here, the peak. So you can see the peak we have here is just above 2 GHz. And let's enable relative marker here. So we go to marker, let's change the mode to delta, and let's actually take a look at the other one, the third order products here. I stop the trace and enable the marker table so you can see things a little bit clearly. And you can see here, essentially we have this peak frequency at 2 GHz, that's at minus 20.79 dBm. And then we have this delta marker, which is 13.9 kHz away from the main peak. And with respect to the main peak, the amplitude is at minus 72.1 decibels. So this essentially is a dBc figure. If you do the math, you can actually calculate the third order intercept point. And the calculation essentially is this minus 20.79 plus half of that 72.1. I'll put the exact number down here, but roughly it's around 15 decibels. So that's how you manually calculate the TOI using a standard spectral analyzer. But of course, we have built-in functions, so let's actually take a look at using the advanced measurement function instead of doing it manually. So let's actually enable the trace again, and let's go to spectral analyzer. And you can see within the spectral analyzer category, we have all these functions. I showed some of these last time, but what we're looking at today is this TOI measurement. All right, I just adjusted some of the parameters. Originally, the span was too wide, was at 20 megahertz. That's gonna take forever for the scan to finish. So I reduced it to 100 kilohertz, like what we did before. And currently the resolution bandwidth is set at 100 hertz. The beauty of this TOI module is that everything you can see here is automatically calculated. I didn't have to do any of the marker stuff. I didn't have to do any of the analysis. All the numbers are shown here. And you can see here, we have the upper tone here at roughly minus 21.8 dBm and the lower tone at roughly minus 23 dBm. Of course, we have the lower third modulation product and upper product, and here are shown accordingly. And here we have the calculation of the TOI, roughly at 13 dBm, which is very close to what we manually calculated before. When I did it manually, I actually didn't do any averaging. I just did it using a single frame. So you can see the delta actually here is roughly at minus 69 to minus 70 dBc, which is a little bit lower than what we had before. What we measured before, I think, was minus 72 dBc, and that's why the TOI calculation is slightly different. Of course, the TOI measured here is due to the non-linearity of the front end of the spectral analyzer. Now, this spectral analyzer also has preamp built in. So what I'm expecting here is if I turn on the preamp, the TOI number probably will get worse. So let's actually take a look at that. So I come back here, I turn on the preamp. And as you can see immediately, now the preamplifier is on and the TOI number dropped. And that makes sense, as now we have an additional amplifier in the signal path. So remember this number with the preamp on, the TOI is at 8 dBm. So let's turn it off again. And you can see that without the preamp, we improved to roughly 12 dBm. For all intents and purposes, anything above 10 dBm is considered generally a good TOI number. So now you know how to measure the third order intercept point using the UTS3000A series signal analyzer. Of course, you can do the same measurement with any spectral analyzer. You will just have to do the math yourself, like what we did earlier. These advanced measurement options of this UTS3060A certainly makes the measurement a lot easier. If there's anything else you guys wanted to see with this UTS3060A while I still have it, please leave me a comment. Alright, that's all for today. I hope you enjoyed the video and learned something new. If you liked it, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. If you wanted to further support my channel, please consider becoming a member. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.